Hello everyone, we will be going through your lecture for week 7, and from week 8 onwards it's going to be all about graph, which is very fun. Okay, but for your week 8 lectures, we are going to look at something which in my opinion is one of your most interesting algorithm for 2004, right? So what you're learning is what we call a Bowers-Radius transform, right? BWT is something which you will never find in an Bachelor of IT syllabus, right? And it's an algorithm which is amazing, right? And you have multiple applications. So we are going to go through about why is BWT awesome, right? And we are going to focus about what are the awesome implementation and application about it, right? So once you have a BWT, what can you do with it, how amazing it is, right? Then in the nature of all of our algorithm unit, right, you're going to learn the first implementation, which is O(n) cube. Then you're going to learn to perform it in O of n, right? O(n) square, right? And O(n) square slash O(n) cube depends on how you implement it. Okay, so it's a really amazing algorithm, right? Seems complex, but once you understand it, it's very easy. It's definitely coming out in your exam, right? It used to be one of your assignment question in the past in combination with surface array, but since we have reduced the number of assignments, we removed the mid-semester exams, right? Because a lot of complaints about too many assignments, right? It's something which you're going to lose out on. But if you have the time, I will really hope you implement it. It's something which, in my opinion, you want to have in your portfolio when you showcase it to some of your interviewer. Okay? So you're going to learn what is BWT, okay? But you're going to learn it from the first application point of view, compression. Okay, so yeah, in an algorithm unit, you're learning an algorithm to perform compression, right? So when you build a BWT string, you can actually compress it very efficiently, right? And most importantly, right, why BWT is awesome. It is actually used for search. So in week 7, we have learned about strides. We learned about suffix tree, right? And in week 6, we learned about surface arrays, right? Is it week 6? No. In week 6, we learned about strides, surface arrays, right? Which we perform retrieval. Okay, so BWT is able to perform retrieval very fast in O of m, right, where m is the length of the pattern itself, right? So whatever you want to search, it will give you a search as fast as a try, right? But you can search on compressed string, right? So if you remember a try, the space complexity of a try is actually O(n) square, right? If you convert it into a string, you can reduce the complexity to O of n, okay? But because BWT, you're compressing it, it's actually less than O of n, right? And you realize you can perform search on something which is compressed, which is freaking amazing, right? You can search on compressed string, okay? So, compression, right? Compression, why is it important, right? When you submit your assignment, we ask you to compress it. When you look at your videos, right, your songs, right, you have your flag, right? Of course, you have your linear, right, and then you have your flag, right, and then you have your MP3, okay? So here, right, is somewhat a lossless compression, right? So if you're an audio file like me, right, you will only count a flag, right? But some of you who is not an audio file, you will usually prefer like MP3, right? Because the file size is much smaller. My flag, a song can goes up to 100 megabyte, right? The same song in the form of an MP3 is probably 5 megabyte, right? But here, when you compress, is what we call a lossy compression, right? You will lose some information. Okay, the nice thing about a BWT compression is it is actually lossless. So you're able to reduce the amount of memory required, but you are still able to maintain the same level of quality, right? And your Spotify will be somewhere here, right? And your Tiger of high res, it should be somewhere in between a FLAC and a MP3. Okay, so compressions are very, very useful, right? For example, if you finish your degree in Monash, right? All of your syllabus, all of your assignments, right? They take up a lot of space. If you know you are not using it often, you're going to compress it, right? So you have more space and everything is very nice and neat. Okay, so compression are actually very, very common, right? And one of the most common compression technique is what we call a run length encoding. Okay, and it's a very simple lossless compression, right? Each character, right? Each character is actually, right, one character. To save one character in memory is actually 8 bits, right, or 1 byte, right, in general. Why? Because your ASCII, if you remember, is from 0 to 255, right? So to save one character is 1 byte. So if you see my string here, right, if we were to ignore the spaces, I have a total of 48 characters. Means the amount of memory required is 48 times 8 bits, right? Or 48 times 1 byte. Okay, so this is the amount of memory which we are using, provided if we ignore space, right, to actually save my string. Okay, then the concept of run length encoding is actually quite simple. Okay, if I want to save A, right, if I got 5 A's, means I will be 5 times 1 byte, right, which is 5 bytes. Okay, I can also save it in the form of 5 and A, right? If I save it in the form of a string, it's the same as 2 characters, right? So times 1 byte is only 2 bytes, right? So you can see it is actually much more efficient. Okay, but if I were to not save my 5 as a string, right? Let's say my 5 is an integer followed by another string. Okay, 5 in bits is 101, right? So 101, right, is actually 3 bits, right? Plus A is 1 byte. Okay, so it will now be 1 byte and 3 bits. Okay, so the nice thing is all of the numbers themselves, right, can actually save a lot of memory. So when you move on to 3155, you're going to learn some of the fastest compression algorithms in the world, right? So you're talking about the ones which are actually used in real world. But fact not, your BWT is also used in the real world. Okay, so the problem is if you were to look at an English language, how could I clear it off? Okay, never mind. I guess I need to manually clear it. Okay. If you look at a normal English language, you realize your alphabets are not joined back to back, right? So in the example I showed you earlier about A, which you can convert to 5A. Okay? In an ideal scenario, right, it makes sense. I save a lot of memory. But if you look at the English language, you realize it rarely happens, right? Because you have your vowels and your consonants, is it? Right? They are actually used in combination, right? For example, IS, right? Uwu, right? Unless someone will type like hi, right? Which is not really a proper English language, right? So if I use run length encoding, right, you realize I'm not saving a lot of memories here, which is a little bit pointless. Okay, then someone came up with a brilliant idea. Why not if I were to group similar alphabet closely? So just like your assignment 1, when you sort something, you group up similar alphabets, right? So here, if I were to sort my entire string, ignoring the spaces, right, we'll see my H, my I's, my M, my O, my B, my R, my S, and my T, and my Y. Okay, they are all grouped up. So if I use my run length encoding, you realize instead of having I, right, I glitch, text to speech combination, right, it can be as simple as forgetting I. I'm saving a lot of memory. Okay, so if you can see here, instead of 48 characters, right, which is what you see, I'm able to only reduce it to 20. But we are going to have a problem. Okay, number 1, right, sorting is very bad. Complexity of sorting, you have already learned your regis sort, your grid sort, your merge sort, right? They are actually very, very high complexity. Okay, yes, we know how many alphabets we have, but we do not know the ordering, right? For example, here, I can rebuild my string very easily, right? If I were to start off here, okay? I know it's M-I, I have Q S, I have Q S, I, right? I can rebuild Missy, right? Then I have Q P, P P, then followed by a I, right? You can see I can rebuild a Mississippi. But if you see here, right, when I build back, it doesn't give me my original sentence, right? Means we lose our original arrangement, and it doesn't make sense. Imagine you have a photo or you have a song, you compress it. When you uncompress it, it's something else. It doesn't make sense. Okay? So, for compression to work, we have two requirements. Number 1, we want it to be smaller. But number 2, we need to rebuild the original one. Okay? So, that is where your BWT comes in. Okay, BWT actually meets both requirements. Number 1, you're able to make something large to be smaller. Number 2, when you decompress it, you're going to obtain back your original string. Right? If you're someone who use a linear system or you use a Mac, which is linear anyways, right? There's something called the bzip. Right? B in your bzip actually stands for BWT. Okay, so you're learning something which is being used in linear system worldwide. Okay, and the original string here, right? This is Mississippi is curry, is this Mississippi is squee, right? Your BWT will be in such a form. Okay, and note I actually added an additional character, right? Which is my terminal, which is what we have learned earlier, right? So it's going to end in the form of a terminal, right? And if I were to do a run length encoding, you realize I only have 40 characters, right? And it includes the additional one, right? Instead of 49, right? Because of my terminal. So I managed to save 8 characters, which is times 1 byte. I managed to save 9 bytes, right? Or 72 bits. Okay? And if I were to use a real world example for an English sentence which makes sense, I'm going to compress it much, much more. Okay, so what you're learning is how to generate, right? Given the original string here, this is Mississippi, blah, 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 how to generate what you have here and compress it. So one of your previous assignments is we give you a very big file. We are talking about 100 megabytes and we ask you to compress it, right? And the way we usually mark it is to see number 1, is the space smaller? Number 2, am I able to decompress it? Right? It's going to be the same as your assignment in 2020sem01 as well, when you learn more complex and advanced compression algorithms. Okay? So, what is a BWT? It's a very, very popular exam question. You should expect such an exam question anyways, right? And it doesn't matter if it's open board or not. If you know how BWT works, you should be able to generate a BWT string. Okay? So, let me try to explain what it is. If I give you a string, let's say apple, okay, you're always going to add a terminal character, right, to mark the end of the string. And what BWT actually does, right, is going to move similar alphabet closer. Let's not use apple, right, let's use banana. Okay, so if I were to do the following, right, you realize I will group my A's to be closer, right? So I will move similar character closer. And because my characters are closer, right, I can now go run length and go in, okay? And most importantly is my BWT of my string, okay? This is my string. Okay, this is my string. Okay, I'm able to get back the original form easily, right? So let me show you an example. If I have a string, why am I always writing script? So who used to programming the one where you open file and remove the following characters at the back, right? So if I have the string, right, let's not use string, let's use gets because we are going to perform packet matching, okay? If you use a BWT of gets, right, I'm going to obtain, let's say x, for example, right? Then I can reverse the process for x and obtain back my gets, okay? So I can do it without a key. It's very different from your encryption, decryption, right? But I can use it in the same way as well. But of course, it's not safe. Okay. So how are you supposed to generate it? Right. Let's use a very simple example. Right. I get a string which is apple. I add in a terminal character at the back. Okay, then I want to form every cyclic representation of a string, right? So A, B, B, L, E, terminal, right? So this is a cycle. So the first one is A, B, B, L, E, right? Which is what you see as the first one, number 1. Okay, then I'm going to start from the next alphabet and go cyclic again. B, B, L, E, terminal A, right? Which is my second one. Then I'm going to do the same step from the next alphabet and go one cycle again, right? B, L, E, terminal, and so on. So how you generate it is very simple, right? I begin my I from here, right? If I were to use numbers, 0, 1, 2, 3, 4, 5, right? I begin with I from 0 all the way to 5. Then I begin from I from 1 all the way to 0. Then I from 2 all the way to 1. Right, then from I to 3 all the way to 3 to 2, right, then 4 all the way to 3, then 5 all the way to 0, right, that's all, okay, and I can know this because my length equals to 6. So what you call here is the cyclic representation of a string, right, which is why I draw out your cycle earlier. Then we will save off the string. What is the complexity? Right? To generate of it, I have n number of cyclic permutation. Okay. Then each cyclic permutation is of length n. Right? So if you see here is n and here is also n. Right? That's why my complexity is O of n squared. Right? If I want to generate of it. Then to save off it, once again, it will also be O n squared. But you can use suffix array, right? If I equals to 1 all the way, if I equals to 0 all the way to 5, right? 0, 1, 2, 3, 4, 5. Okay, so it will be 0, 1, 2, 3, 4, 5. Right? For example, 3 will be 3 all the way to 2, right? So what I'm going to do is I'm going to just loop, right, from I equals to 4, right? Then so I equals to 3, 3, 4, 5. I reach the end of the string, 0, 1, and 2, right? you realize my length is the same. So instead of saving off the alphabet, because it's cyclic, I know it is continuous, I can only save my suffix ID, right? So because of that, I can reduce my space complexity to O of n, right? So from now on, in every implementation and also in your exam, we do not want to see you generating it if we ask any question about complexity, right? Because if you were to generate it, it will be O of n squared. If I were to generate it as a suffix ID, right, over here, it's only O of n, right? So it is much more space efficient. Okay, so once we have off the string, we are going to sort it, right? So you know a suffix array, right? You know a suffix array is your suffix ID in order, right? So instead of me manually sorting my apple, right? So if I were to sort it, right? If I were to perform a Regis sort or whatever sort, right? It's going to be color A, B, B, L, E, followed by A, B, B, L, E, terminal, right? Followed by E, terminal A, B, B, L, followed by L, E, L, E, wait, L, E, terminal A, B, B, right? And finally will be B, L, E, terminal A, B, and B, B, L, E, terminal A. Okay, so if I were to attach their number, it will be 5, it will be 0, E is actually 4, L is actually 3, right? B, L is 2, and B, B is going to be 1, right? What you see here, if you remember from last week's lecture, is your suffix array, right? So instead of sorting my alphabet with Regis sort, right, counting sort, counting sort doesn't work, Regis sort, heap sort, grid sort, merge sort, bubble selection, insertion, right? We can just do it by generating our suffix array, okay? Then the last column is actually, right, the last column is your BWT, okay? So if my cats equals to A, B, B, L, E, terminal, right, my BWT of cats will be terminal A, B, B, no, wrong one, right? It's the last column, my bad, not last column of that because it's not sorted. So it's going to be E, terminal, L, B, B, A. Okay, so this is my BWT string, okay? And I can know it for my suffix array, right? Because if it begins with 5, means it ends with what? Right? If it begins with 5, it ends with 0. If it begins with 0, it ends with 5. If it begins with 4, it ends with 3. If it begins at 3, it ends at 2. If it begins at 2, it ends at 1. If it begins at 1, it ends at 0. Okay, how does it work? Okay, it's the following, right? So if this is the ID, right? If this is the ID, it will be ID minus 1. Okay, so if it is 5, 5 minus 1 is 4. If it is 0, because it's cyclic, 0 minus 1 is negative 1. Negative 1 is the last alphabet, which is 5. Right? 4 minus 1 is 3. 3 minus 1 is 2. 2 minus 1 is 1. 1 minus 1 is 0. Then you look at the alphabets here. Right? What is the fourth alphabet? Fourth alphabet is E. What is my fifth alphabet? Terminal. What is my third alphabet? L. What is my second alphabet? B. What is my first alphabet? B. What is my zero alphabet? A. Right? You realize it is the same. So the entire step is very simple. Right? So get a string A, B, B, L, E, put in a terminal, right? you can generate all cyclic implementation. Over here, I want you to use a suffix ID. Okay. Then when you sort it, I want you to use a suffix array, right? Then once you have the suffix array, right, which is what you see here, we are going to just use, right, here's the suffix array. We are going to just use the last column, right, and we are going to F it. Okay, a very, very simple concept of suffix ID minus 1. Okay, so if we were to look at your Mississippi, right, if I were to sort it, I will obtain the following, right, and the last column will be my BWT string, right. But if we were to make use of the suffix array, right, if we use a minus 1, we should already have our final one. Okay, so which is why you learned about suffix array last week. Okay, so let's go through a very simple example, right? BIRG terminal. Okay, so you in your programming, you're not supposed to generate a cyclic permutation, but since we are not doing programming, right? BIRG terminal, right? RG terminal, right? Then it will be G terminal, right? BIRG, BIR, BI, and it will be B. Okay, so what you see here is the cyclic permutation. If I were to use my suffix ID, right, suffix ID, it will be 0, 1, 2, 3, 4, right? So it will be the same as if I put a terminal 0, 1, 2, 3, 4. Then if I were to sort it, right, if I were to sort it, I'm going to obtain terminal BIRG followed by BIRG terminal, right, followed by G terminal BIR, right, then followed by IRG terminal B, and the last one will be RG terminal BI, right? So I know this because if I use my suffix array is going to give me 4, 0, 3, 1, 2, right? Then here, if I want the last alphabet, it's just minus 1. 4 minus 1 is 3. 0 minus 1 is negative 1. 3 minus 1 is 2. 1 minus 1 is 0. 2 minus 1 is 1. Right? Since it's negative 5 means it will be 4. Right? So what is my third alphabet? Third alphabet is G. What is my fourth alphabet? Fourth alphabet is terminal. Second alphabet is R. 0 alphabet is B. First alphabet is I, right? Right. So it's the same as my last column. So my BWT of BIRG terminal is going to be G terminal RBI, right? Which is what you see here. Okay. So it is pretty amazing. Okay. Now, why does your BWT actually group similar alphabet up, right? It's because of the last and first relationship. So if I say the last, right, if you see here, this is my last, here is my first, right? So if you see here, B is because it's cyclic, right? Mississippi, B is followed by I, right? Okay? Then if you see here, okay, my S is followed by I, right? So my S is followed by I. My S is followed by I. Okay, likewise, my S is followed by I. My S is followed by I. Okay, so when I were to sort it, you realize I will group my I's together, right? And what is before my I? S is before, right? What is before my I? S is before my I, right? Guess out I group my similar I's, my similar S together, right? It's the same concept here, right? If you see my SS and my SS, okay? After S, it will be followed by S. After S, it is followed by S. After S is followed by S. After S, it is followed by S, right? Then, if you see here, okay, after S, it is followed by I, right? After, no. Wait, oops, wrong one. It should be here, okay? After I is followed by S. After I is followed by S. After I is followed by S, right? So when we group of the S together, right, we are going to group the I's and the S together, right? It is what your explanation here is, right? So if in the English word, right, is a very common word. I is, you is, we is, blah is, monkey is, right? Is a very common word in the English language. So if we were to look at a string or a sentence or a paragraph, you're going to see the word is occur a lot of time. So if we were to group up them, I will be followed by S, because is. I will be followed by S, I will be followed by S, right? So when we were to sort it based on the S, right, what is before S? Before S will be I. I will group all of the I's together, okay? So because I'm doing such a way, I'm grouping similar alphabets together. So instead of saving I can save it as 3I, right? This is the reason why BWT actually works, right? So if I give you a text, you can run BWT to obtain some, let's call it X, right? And X, you can compress it, right? Compress X into Z. Amazing. Can you reverse the process, right? So I want the reverse of BWT on X to obtain back my text, okay? And this is why it's amazing, right? You know the BWT of Mississippi is IPSSM, right? Which is what you see here, okay? The last column. How am I able to reproduce it back, okay? So if I were to give you the following, right, I know my BWT is the last column, right? So my BWT is the last column. So if I have a last column, right, it will be IPSSM terminal PISSII. Okay? My question is, are you able to produce the first column? And the answer is yes, right? Because we know the first column is in order, right? The first column is in order, right? Terminal followed by I, followed by M, followed by P, followed by S, right? If I use my example here, right, you realize it is in order. Terminal A, E, L, P, P. Okay? So if I were to sort the last column, right? If I were to sort the last column, right? If I were to sort the last column, right? If I were to sort the last column, I'm able to obtain the first column, right? So it will be color followed by how many I's? 4 I's, right? Followed by M, L, M, N, O, P, to P, then followed by 4S. Okay? So if I perform a sorting on the last column, right, which is a very simple counting sort, right, I'm going to be able to obtain my first column. Okay, and I realize I've missed out a slide. Okay, so, right, so note, just now we have the last column. Okay, I can obtain the first column. Okay, but what we want is the first row, right? Because if you see the first row, this is Mississippi. Okay, so if we want to convert IPSSM terminal PISSII, right, back to Mississippi, I will need the first row, right? The first row will be Mississippi. Okay, so this is where it is very interesting, right? If I give you a text, right, let's say if it is Mississippi, right, I can convert it into the BWT, right, and then I can send it as a message. So a senior of yours from 2017, right, have actually posted a video about it, right? So, as I mentioned, if it was an assignment last time, you can click on the link itself, right? And what it have is actually the message here, right? So in other words, the BWT of cats equals to SUNS terminal N. Okay, so you want to reverse BWT -1, right? SUNS terminal N, right, into your cats. What is your cats, right? And you can watch the video here, right? And it is actually a meme which was very popular in 2017. Okay, so it's an old meme. Okay, so here, right, I've shown you, I want the first row. Okay, my BWT is the last column, right? And sorting the last column, I can obtain the first column. The question is, can I obtain the second column, third column, fourth column, fifth column, right? Until I can rebuild back my alphabet one by one. Okay, so we can produce the first column. I've shown you how. Okay, how are we supposed to produce the second column, right? Since it is a cyclic relationship, right, I know there is some form of relationship, right? I is going to be followed by terminal, right? So because it's cyclic, right? It's cyclic. So I know after I, it will be terminal. After P, it will be I. After S, it will be I. After S, it will be I. After M, it will be I. After terminal, will be M. After P, will be P. Right? After I, will be P, and so on and so on. Okay? So because of the cyclic relationship, I can concatenate L followed by, right, concat L and first, right? So this is first, this is last, right? So if I concatenate, it will be L and it will be first. Okay? Which is whatever I showed you here, right? Each one of it is a concatenation. So what happened is, I'm now going to sort it, right? So I'm going to use Registort, and I'm going to use a Registort, and I'm going to sort it. Okay? So you realize, if I have L and first, and I will go sort LF, okay, I will actually obtain back my first, because I know my first is in order, right? I will obtain back my first, because my first is in order. Okay? But what is after first? I know after first is my second column. Okay? So you realize, if I sort first, if I sort last and first, right, I will obtain first because it is in order, right? And the next alphabet is automatically my second. Okay? So this is what's happening, right? I start with only my last column. I know what is my last column. Okay? Then, if I sort my last column, I will obtain my first column. Okay? What I'm going to do now is, I'm going to get my last column and concatenate it. Okay? Then I'm going to sort it. Then I'm going to get my first column and my second column. So now I have my second column. Okay? Then I'm going to repeat the same thing again, right? I'm now going to concatenate my last column, my first column, and my second column, right? Then I'm going to sort it. So what I'm going to get is now the first column, second column, and my third column. Then I can get my third column and reproduce it. Fourth column, fifth column, sixth column, seventh column. Right, so fourth, fifth, sixth, seventh. And what happened is, now I already have my first row, which is my original cats. Right, which is pretty amazing. So sort with the last, sort the last to get the first, right? Concatenate the last and first, right? Remember it's cyclic, okay? And since it's cyclic, right? After I sort it, you know my first column is always in order, because, right? If I sort the last and the first, my last become the first, right? Then my first become my second. Then I concatenate, then I repeat until we have our final string, right? So a lot of words, right? Let's use our Apple example, E terminal LPPA, right? So let me go to my whiteboard, right? E terminal LPPA. Okay, this is my BWT. I know it is my last column, E terminal LPPA. Okay, if I were to sort it, I will obtain my first column, which is terminal A, E, L. Oops. Terminal A, E, L, P, P. Okay, I obtain my first column. Okay, then I concatenate last and first. So it'll be E terminal A, L, E, P, L, P, P, A, P. Right? Remember, it's a cyclic permutation. Okay, then I'm going to sort it. Okay, so here you will use a regi sort, right? What else can you use which is suitable? I would think the most suitable one is usually your regi sort. So after I perform a regi sort, it will be terminal A, terminal A, followed by AP, followed by E terminal, followed by LE, followed by PL, followed by PP. So you realize my first and my first is the same. So what I see here is my second. So it will be A, P, terminal, E, L, P. Here is my second. Okay, then I'm going to concatenate in my last, right, which is E, terminal, L, P, P, A. Okay, then I'm going to sort it. Okay, which will provide me with terminal AP, APP, E terminal A, LE terminal, PLE, PPL, right? Which is my first, second, and third. My third is P, PPA terminal EL, PPA terminal EL, PPA terminal EL. Okay, so I will have my third. Okay, once I have my third, concatenate my last again, right, which is E terminal L P P A. Okay, then I'm going to perform a sort, right, sort it. Okay, so it's going to be terminal APP, terminal APP, APPL, then it's going to be E terminal AP, then it's going to be LE terminal A, PLE terminal, PPLE. Right? If you notice here, I'm starting to go it first, second, third, fourth. Right? So my fourth is PLP A terminal E. PLP A terminal E. Now I got my fourth. Okay? Once I got my fourth, same thing again. Oops. Right? Put in a first. Put in the last. Remember what is my last? My last will be E terminal LPPA. Okay. Then once again, I'm going to sort it. Right? It's going to be terminal APPL. As you can see, I'm starting to rebuild it very nicely. Followed by APPL. Followed by E terminal A. Oops. Wait. A wait first. Right, A, P, P, L, E. Yeah, I missed one. E, terminal A, P, P. Then followed by L, E, terminal A, P. Followed by P, L, E, terminal A. And followed by P, P, L, E, terminal. Last column again, L, E, P, P, A, terminal. L, E, P, P, A, terminal. L, E, P, P, A, terminal, right? And here will be my, right? So what you see here is going to be my first, second, third, fourth, fifth, right? Since A, P, P, L, E terminal only have 6 alphabet, my 6th one will automatically be my last, right? This is where I am. So if you see here, can you look at my first row now? A, P, P, L, E, right? So my gets equals to A, P, P, L, E, coming up. Easy, right? Okay. So, pretty amazing, right? Only from the last column, I can generate the first column, second column, third column, fourth column, fifth column, sixth column, seventh column, all the way until n-1 column. Okay? Then the first row will be my original string. Okay, and the reason why it works is because it's cyclic vocation, right? And we are making use of the groomers, right? Not groomers, it will be gamers, right? So here the groomers will be AP, PP, PL, LE, E terminal, right? And also because it's cyclic, I'm going to have the last one, which is terminal A. Okay, which is what you see here. So if I were to sort everything here, right, I will obtain back the first and the second, right? Then for the streamers, it's the same concept, 4mers, 5mers, 6mers, and so on, right? So, right, concatenating last, first, and second give us streamers, right? Concatenating last, first, second, and third give us the 4mers, 5mers, 6mers, all the way until the mers, right? Once we reach the mers, we are going to have the ultimate product. We are going to have the entire matrix, and our first row is the original string itself. Perfect. Okay, so what is the complexity? Okay, you realize if I go from first, second, third, all the way until last, right? My last is technically my end, right? If my cats is from 1 all the way to n, right? 1, 2, 3 all the way until n. Okay, so I know I'm going to have n number of columns, and I need to sort it n times, right? Because sorting the last gives me the first, right? Then concatenate, then sort again to get back the third, and so on. So I'm going to have n number of, right, sorts, right? And each column is going to have n number of characters. Okay, so my entire complexity is going to be O n cubed, which is a very, very, very high complexity. Okay, so yes, it's very, very amazing. It's very, very awesome, right? Where I only need the last column, I can obtain the first column, second column, third column, and my first row is my answer, right? But the problem is, doing it is really, really long, right? You saw me working on my whiteboard earlier, right? You saw me sorting, right? Even me doing it as I'm explaining is a lot of work. Okay, so blah 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 gives the explanation of the complexity, right? And to make it worse, I need to save all of the string, which is O n squared, right? So a lot of work, a lot of effort, right? But remember, why are we in computer science? Because we learn to be lazy. Okay, so I'm going to show you a way to reduce from O(n) cubed into O of n. Reduce the space to also be O of n. Wow. Okay, and this is why it is totally amazing. Okay, so you can take a break first, right? Go grab a snack, right, or whatever you want. Get a break, because when you come back, I'm going to blow off your mind. Okay, and show you how amazing it is. Okay, so have your break. Okay, welcome back from your break, and let us begin. Okay, so you're not going to learn to convert inward, right, from BWT of a let me just go x equals to BWT of x. Okay, so you're going to convert BWT -1 of x back to x. Okay, so if we were to look at Mississippi, right, if I were to show you the matrix, this is what you're going to see. Okay, I'm going to explain a few observations from your matrix, right, and from the observation itself, you're going to understand why is the shortcut, right, which is the O of n version, very, very fast. Okay, so let's see. You know the last column is your BWT string, right? You know the first row is where your original string is, right? Only difference is your terminal is at the front. Okay, then you also know the first column is the sorting of the last column, right? It will always be in order. Okay, so I want you to look at the eyes, right? You realize on the left I got 4 eyes, right? Okay, the point of 4 eyes is love. Okay, then if you look on the right, you're going to realize you are also at 4 eyes. Okay, but I want you to get a note at the eyes, right? Get a note at the eyes, right? I followed by terminal. Okay, I followed by terminal. It's the same as I followed by terminal. I, right? I followed by P. I followed by P. I followed by S. I followed by S. Okay. Then last one, I followed by S. Okay. I followed by S. Oh wait. You realize the order of your eyes in the first column is the same as the order of your eye in the last column, right? Their order actually follow, right? Because of the cyclic property. Okay, the cyclic property ensures stability. The same as the S, right? S followed by I, Si. S followed by I, Si. S followed by S, Ss. S followed by S, Ss. Oh wait, it is the same thing. Okay, so if I were to put a number, right, first I, second I, third I, fourth I, there's only one M, right, first P, second P, first S, second S, right, you're going to get such a pattern, right? And it is such an observation which will allow you to do an approach which we call LF mapping. Okay, what we call the LF mapping. Okay, what LF mapping does is you map the last with the first, right? So S3 will be mapped to S3, L4 will be mapped to L4. Okay, this is what we call the LF mapping. Okay. Blah blah blah. This is the same thing I've explained, but I think I explained better. Okay, so will we require the first column? The answer is no, right? Over here, I shown you the first column as a visualization, right? But when you were to implement it, our first column is not required, right? Why is the first column not required? I only require a rank table, right? And how are you supposed to build your rank table, right? The first one is always your terminal, right? So after first one, it will be the second position, right? Second position will be for I, right? Which is the next smallest lexicographically, right? The next lexicographically smallest character, right? Which is cool. How many eyes do I have? 1, 2, 3, 4. 4 eyes. So the next position will automatically be 6. Right? Then here, right, I only have 1 M, that's why it goes to 7. I got 2 P, it goes to 9. Right? So you can see, right, I do not need the first column, because if I have the first column, I need ON memory. Right? I will need ON memory. Which is a waste of space. What I have here is only OM, right, where M is the number of unique character. From A to Z, my M can only go up to 27 as the maximum. Perfect. Okay? So, how we do it is just to count the frequency, and we can use the frequency to build it very, very quickly, and the complexity is O of N, right? So I'm going to show you how it actually happens, right? Here, my unique character is actually terminal I, M, P, S. Then I'm going to loop count, right? I have 1 I, initially is 0, right? Now I have 1 I have 1 P, I have 1 S, I have 2 S, I have 1 M, I have 1 terminal, I have another P, I have another I have another S, becomes 3, I have another S, it becomes 4, another I, right, oops, right, 3 and 4, okay? So what I have here is what we call a frequency table, right? So at the end, I'm going to have 1 S, 4 I, 1 M, 2 P, and 4 S. Okay, so this is the frequency. Okay, then I'm going to use the frequency to build my rank. So I begin from rank 1. 1 plus 1 is 2. 4 plus 2 is 6. 1 plus 6 is 7. 2 plus 7 is 9. You realize it is exactly the same. Exactly the same. So what is my complexity? I loop through everything in O of N, right? So as I loop through, I update my table, right? So if I generate an array from terminal A, B, C, D all the way to Z, right? It's size of 27. I can access in O of 1. My complexity is only O of N, right? So to build this table is O of N. And then, right, I just loop through my O of M table, right? This is O of M, and I just sum it up. Here is O of M. So my total complexity equals to O of N plus M. But I know my M is constant, 27, because I have 27 alphabet. So my total complexity is only O of N. Okay? So I now have a rank table. Okay? Once I have the rank table, this is how I'm going to perform my my LF mapping. Remember, it's called LF mapping. This is the official name. Okay? I begin with the first row. Right? Terminal is mapped to L. Right? Terminal is mapped to L. So I know, right, because of the cyclic property, before terminal is going to be L. Before terminal is going to be I. So I will put I before my terminal, which is what you see here. Okay? This I is the first I. I will map over here. Okay? The formula is very simple. The rank of I is actually 2. And the order of I, which is 1, will be 1. Okay? Then I need to minus 1. Okay? So 2 plus 1 minus 1 is 2. then I can find the I again. Perfect. Okay. And then, okay, it is mapped to P, right? So I will prepend a P. Okay, I will prepend a P. Okay, and how am I supposed to find it? The order of P is 1, right? The rank of P is 7. So 7 plus 1 minus 1, right? Because of my formula, I will find the exact P. Right. Then I map it to another P, I prepend a P. This is school, my rank of, right, school, and my rank of P is 7, right? 2 plus 7 minus 1 is 8. I'm able to map it, right? Then the next one will be I, and so on, and so on, and so on. Okay, so as I perform the mapping, you realize I'm just going through my traversal, right? And you realize each operation, I will add one alphabet. Okay, each operation, I will add one alphabet. So the way I add my alphabet is very simple. I'm going to initialize an array from 1 all the way to n. Right, then I will put terminal, right? Then I will put I, P, P, I until I reach the first alphabet, which is n. Okay, note complexity of prepend is O of n, right? So in order for me to avoid my complexity of prepending n times, which will give me n squared complexity, I first initialize an array and I can prepend in O of 1. Okay, so my complexity is going to be just O of n, right? Because what is happening here, right? What is actually happening here? I will go through every position one by one. I will go through every position one by one. In total, I only have n position. Means I need to have O of n operation. Each operation is just performing maths, which is O of 1. Okay, so my complexity will be O of n multiplied by O of 1, right? This is my maths, right? Plus 1. This is my prepend, right? Remember the prepend, we use an array, right? And then we just put it in. So you realize my overall complexity is only O of n. Okay, it's totally just O of n, right? And the only thing I need is only my rank array and also my last column. Okay, so let me show you how I can do it, right, with the original thing of bananas, right, which is A and M B terminal AA. A and M B terminal A. A and M B terminal. Okay. A and B. A and M B. A and M B terminal AA. Okay. So let us begin. Remember what I said? I only need my last column, right? Which is A and B terminal AA. Okay? Here is what I call my count. Okay? And here I'm going to have a rank array, right? My rank is going to be from terminal all the way until Z, right? So here I'm going to have terminal A, B, blah, 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 all the way to N, and that's all. Okay? So what I'm going to do is, right? Oops. Let me go here. This is count. This is rank. Okay? Let me draw out nicely. Okay, then I'm going to create an order array. Okay, my count will be initialized to 0. Okay, and then let us begin our maths. Okay, loop through my last column, right, which is the same as me looping through here, right? So the first alphabet is A. Increment the count of A by 1. Next alphabet is N. Increment the count of N by 1. Next alphabet is N. Increment it by 1. Next alphabet is B. Okay. Next alphabet is terminal. Next alphabet is A. Next alphabet, wrong one. Next alphabet is A. Okay. Next alphabet is A. Right. This is my order array. It's the same as me doing the following. Right. It is the same. So there's really no point of me doing it here. Okay. Now let us look at the rank. Right. I know I always begin from a rank of 1. 1 plus 1 is 2. 3 plus 2 is 5. 1 plus 5 is 6. Right. Let's just put 6. Right. Remember we have a lot of alphabets. Then 0 plus 6 is 1 plus 1 is 2. 3 plus 2 is 5. 1 plus 5 is 6. 0 plus 6 is 6. 2 plus 6 is 8. 0 plus 8 will be 8. Right? So imagine if I got the first column, terminal A, B, N. Right? If I were to put numbers, good ends. Okay? It will be 1, 2, 3, 4, 5, 6, 7. 1 plus 1 is 2, right? Okay. 2 plus 3 is going to be 5. Wait, how many ends do I have? 6. Yeah, correct. I was blurred. Okay, so you see the rank of terminal is 1. The rank of A is 2. The rank of B is 5. The rank of N is 6. Okay, it totally match. Okay, so you realize I could not actually need anything else. Okay, then the formula is going to be, right, rank of X plus order of X minus 1. Okay, so let us try to rebuild our original string. Okay, I'm going to rebuild it here. So let me use a black ink. I begin with terminal. Okay, my first alphabet is A, right? My first alphabet is A. A have an order of 1 and a rank of 2, right? So it will be the rank of X plus order of X minus 1, right? So the first alphabet is A. Let us put A, right? So it will be 1 plus right? So X equals to A, right? Okay, so order of A is 1, rank of A is 2. 2 plus 1 minus 1 is 2, right? So let me just put numbers. 1, 2, 3, 4, 5, 6, 7. Okay, so it'll be easier. Okay, so here I will move to position 2, which is here. My alphabet is N, right? Order of N is 1, rank of N is 6. 6 plus 1 is 7. 7 minus 1 is going to be 6. So I will go to position 6, which is A. Okay, order of A is 2. Rank of A is 2. 2 plus 2 minus 1 will be 4. Wait, it will be 3. Right, 2 plus 2 is 4. 4 minus 1 is 3. It will be N. Okay, Then order of n is school, rank of n is 6. 6 plus school is 8, a minus 1 is 7, right, which is a, right. Order of a is 3, rank of a is school, 2 plus 3 is 5, 5 minus 1 is 4, right, and I realize I will have a b, okay. Then order of b is 1, rank of b is 5. 5 plus 1 is 6. 6 minus 1 is 5. I go back to L, which is coming out. Right. So this is when I actually terminate my program. Right. So you realize my complexity is just totally O of n. Right. To build the order array is O of n. At the same time, I build my rank array, which is also O of n. Then for me to perform my LF mapping, to rebuild this is O of n because my formula is O of 1. Easy, right? Of course, here I purposely begin from 1. If you're programming, you're going to begin from 0, right? So how are you going to convert from 1 to 0? I'll let you figure it out. Just for fun, of course. Okay? Pretty amazing. Okay? So, we have learned how to generate a BWT string. We have also learned how to reverse it. Okay? And now, let us go through one application scenario. Okay? For this, I actually prepared a comic. And for some of you who are Zoomers, right, I'm not sure if you know CSI, right, so this is actually a template for the CSI meme, okay? So, imagine you're in bioinformatics, right, or let's say it's the police department and someone got murdered, right, and usually what you look for in the crime scene is for any form of DNA samples of who the killer may be, right? If the DNA sample is found, right, I can use the DNA samples and search it through a list of suspects in my database, right? Then if I find someone with the same sample, means that someone was at the crime scene and means that someone is probably a murderer, right? But if you came from a police point of view, right, I have a database of all my suspects, right, n number of suspects. And if you're a very large country, for example, US, your population is in millions. Imagine a database of millions of humans, okay? To make it worse, a DNA sequence is very long, right? A DNA sequence is very long. It can be made out of the 4 proteins, T, G, C, A, right? Yeah, right. So it can be T, C, C, A, G, T, A, C, right? It's very, very long. Okay? Let's call it M. Now imagine if you want to search through O of NM, where your n is millions and your m is billions. It is very, very slow. To make it worse, for you to save everything is actually a waste of memory. So you want to compress it. How do you compress it? BWT, right? You bzip it. Okay? So, right, the DNA sequence are actually compressed, right? And then we want to search it very easily with a with your BWT, right? Imagine my cats, right? It's actually Mississippi, M-I-S-S-I, Mississippi, if I'm right, right? Which is the same one. But you realize I do not need my cats at all, right? I only need the BWT, which I am able to compress, okay? Then Mississippi, Okay, am I able to search for Cs? Right, if you see in the original string, SIS actually exists, right? Cs actually exists. Okay, but if you see in my BWT, you're not able to find your SIS. So the crazy part about BWT is I can search for Cs inside, right? And this is how it's going to happen. Okay, once again, it's only for visualization, right? I show you everything. In reality, we only need the last column. Everything else is totally not required, right? I only need my last column. Okay, so the concept is very simple, right? What you see here is what I will call my search space. Okay, at the beginning of every search, our space will be from the start to the end, from 1 all the way up to n. Okay, and we want to search for Cs, SIS. When we search, we will begin from the back to the front, right? Because it's a cyclic relationship, right? And we know the last column is the last alphabet. Okay, so, right, we search from the back, right? Let's look for the S inside my search space. The first S is over here, and the last S is over here. Right, so first S is at index 3, and the last S is at index 10. How are we supposed to find it? Remember earlier, we have the last, and we also have order, right? So, we are able to find it very easily. Okay, if you look at your lecture notes by Daniel Anderson, that's actually a formula. You just apply the formula. It's very easy, right? In your exam, you do not need to apply the formula, so you can include it like what I show you, right? So the first S is S1, the last S is S4, right? So I can find my S1 to S4, okay? Which is what you see here. Okay, so I've already found the substring of S out of SIS. Okay, and I know it's S1 and S4. Okay, so S1 and S4. Then what I'm going to do is I'm going to reduce my search space to the following, right? Because S1 is at position 9, S4 is at position 12. So my search space from the very big, it will become so small. Okay, then I search for the next alphabet, which is I. I have one I, right? The first I is I3, the last I is I4. Okay, so where is I3 and I4? I3 and I4 is over here. Okay, so what is happening here is, if you see here, I found IS. So I've already found the, in SIS, I've already found the IS, which is nice. Okay, then this is my new search space. I search for the last alphabet, which is S. Okay, where is the first S? Over here. Where is the last S? Also over here. Means both pointers are pointing to S2, right? Which is here. So if you see here, I found SIS, right? I found SIS, which is the same here, SIS. Okay, so if I were to write Mississippi, MISSI, SSIPPI, terminal, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, where is SIS? Right, where is SIS? Okay, where is my SIS? My SIS is over here. Okay, you see here is the second S, first S, second S. Okay, so not only am I able to know if the substring exists or not, but I also know the position, right? Because this will be S1, this will be S2, right? My second S is actually at here, right? That's where my second S is. Okay, so if I were to do a surface array, right? So my S2 is in position 4, right? If I go create another position, right? If you see, if I have a surface array, right? My surface array here is going to be 12, here is going to be 11, here will be IP is going to be 8. Okay, then it will be SI, right? This will be the this is the second S, right? No, wait, I3. Which one is I3 already? Wait. Let me, this is 12. Yeah. Wait. You know what I said earlier, right? So let me just write down your surface array. This will be 12, right? This will be this will be the 11. This will be IP. This is the surface ID of 8. Then here will be ISSIP. It will be 5. It will be ISS. It will be 1. Right? Wait, no. It will be 2. My bad. It will be 1. Then here will be BI. This will be gang. Then this will be BP. It will be 9. It will be SIS. It will be 7. Then it will be SISS. It will be 4. Then 11 will be SSIPP. It will be 6. And it will be 3. Okay, so if you see what I'm showing you here is a surface array. So earlier we found our SIS could be over here, right? We found our SIS could be over here. Means the surface ID tells me my substring begin from position 4. That's why I can find SIS. Right? In all the S1, S2, S3, I got confused. Right? You find based on your surface ID itself. Okay? So let me just write this down very quickly. Notepad plus. I just open a notepad. Okay. This is annoying. Go to my. Okay. This cut. Okay. Let me just. First I I'm going to see server. Okay. No, I accidentally remove it by accident. Okay, I fine. Okay, let me just re-go it again. Okay, let me just go to the next one. Right, yeah, I found my SIS. Okay, Mississippi, MISSI SSIPPI terminal 1 2 3 4 5 6 7 8 9 10 11 12. Okay, what will be my surface array? Okay, my surface array, as I mentioned earlier, it will be 12, 11, 8, 5, no, 8, 5, and it will be 2, then it will be 1, then it will be 10, it will be 9, then it will be SIP, SIP will be 7, okay, then it will be SIS, which is 4, then it will be SSIP, SSIP will be 6, and it finally will be 3, okay. So let me just write it down one place, 8, 5, 2, 1, 10, 9, 7, 4, 6, 3. Okay, so initially a maximum search space, we search for S, right? The first S is S1, the last S is S4, right? So this is my new search space. Then I'm going to look for the second S, right? I'm now here. Okay, the first S is S3, the last S is S4. So my search space becomes here, right? So I've already found SS, right, which is SS and also SS. Okay, the last one will be I. What is my first I? First I is I3, last I is I4, right, which is what we see here. Okay, so I found ISS, right? I found two occurrences of ISS. So if I were to put my suffix array, remember Mississippi, right? MISSI, Missy, MISSI, SSI, PPI terminal, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. My suffix array is 12, 11, 8. Quite difficult to see, right? Let me just shrink it more first. Okay. 12, 11, 8, 5, 5, 2, 1, 10, 9, 7, 4, 6, 3. Okay, so over here I found ISS, right, which made sense because we are searching for ISS. My first ISS happens at position 5, ISS. Okay, so you realize not only do I know if the string exists or not, but I can also find the position of ISS. My second ISS occur at position 2. Go to position 2, ISS, right? So you realize my complexity is O of M, right? Where M is the length of my pattern, right? We usually call what we are searching for as the pattern, ISS. I just loop through from the M, right? So if my pattern is 1 all the way to M, I loop, right, for I just loop M to 1. Okay, then I perform the mapping. So my complexity will be O of M. Okay, then not only I know if it exists, I also know the position where it exists. I also know how many exist, right? I know I have 2, right? Because 4, 5, right? 5 minus 4 plus 1 is 2. Okay, I also found 2 occurrences, which is the same as the search space here, right? 2. Okay. One last example, MSS, right? So remember, begin the search space, go from the back, right? So from the back, first S is S1, last S is S4. So my search space will be here, S1 and S4. Then search for the next S. First S is S3, last S is S4, right? So I map to here. Okay, so I found SS. Last one, I need to look for M. Do I have any M? No M. No M means not found. That's all. Right, so it's a very quick and very simple process. Right, I can search for it in O of M. Right, if you use a binary search, right, provided if I generate everything here and I perform a binary search, my binary search is O of log M. Here I can perform it in O of M. right? So you can actually see how fast you can search, right? So your BW key, you can see you can compress, right? You can see you can recover. How fast can you recover? O of n. And you can see you can also search in O of m. Right, you realize everything is linear time complexity. Right, binary search, nope. Right, m log n. Right, here it's just O of m. It's so much faster. And if you look at your lecture notes by Daniel Ankerson, it will actually show you the formula. Right, but in your exam, you can do it like the way I show you. Right, how I show you here is how you can do it in your exam. Right, note when you're programming, the first column doesn't exist, and you realize the column in between is useless. Right, I'm just adding it for a visualization. But in your exam, you're free to draw the last column and the first column. But when you implement, you only have the last column, the order array, and also your rank table. That's all you need. Okay, so pretty much that's all. I've covered everything required about BWT, right? So in our tutorial next week, I'm going to be a little bit brief and fast as well, because as I said, I've covered everything. Okay, so hope it has been a mind-blowing experience of you learning BWT, right? And it's not an algorithm you can find in a lot of Malaysian university that you won't find in Malaysian colleges, right? Don't believe me? Ask your friends in some of the college in Malaysia, right? I've known because I've asked before, right? So it's quite an impressive algorithm, right? Okay, that's all. Thank you very much. Bye.